Hello everyone, my name is Soumyadip, a third year EC student. Today I will be present my internship project, which is the EV ADAS Central Command System. This is essentially a real-time electric vehicle dashboard combined with an automated safety warning system built on STM32 microcontroller. It will be simulated in PICSimLab and connected to a live Python dashboard. Let's go on the slide 2. The main goal of this project was to simulate a production-style EV instrument cluster and safety layer entirely in software. I wanted to model real vehicle physics like actual torque, speed, and battery drain instead of just putting fake numbers on a screen. I also needed the system to detect real driving hazard using some ultrasonic sensors, then stream all of that data live to my Python dashboard. It means like that the Python dashboard and the PICSimLab are interconnected with each other. Looking at the high-level architecture, on the left we have our inputs like three ultrasonic sensors, three ultrasonic sensors. Here, here it is the architecture and the virtual sliders for the brake, motor temperature. All of the raw data feeds into the SM32 microcontroller in the middle, which is process the math and transmit it over a connection at UART connection over at 115200 baud. Finally, that will be sent to the Python dashboard, and we can see the received data in the dashboard perfectly. Let's go on the slide 4. So this is the pin mapping and peripherals. Here we can see the PA0 and PA1 for accelerator and the brake potentiometer. Peripheral is ADC. I used analog ADC pins for the brake, accelerator, motor temperature sensor, and for the motor drive, I set up a 20 kilohertz PWM signal. For the safety system, I wired the front, left, and right ultrasonic sensors to port B. Means you can see port 0, PB0 through PV5. Three ultrasonic sensors are there for one for front, one for left, and one for right individually. I also set up a buzzer for audio warnings and four LED lights to give the driver instant visual alerts. The alarm will be PV7, but in live demo I use PV11. Okay. I split the code into two separate control loops. The first loop runs at high, very high fast every 10 milliseconds to handle the driving by reading the pedals, updating the vehicle physics, and turning the motor. And the second loop runs every 100 milliseconds to handle the safety systems by reading the ultrasonic sensors, calculating crash risk, updating the warning LEDs, and sending the data to the Python dashboard directly. So mainly, this is the safety logic is based on a simple formula where time to collision or TTC is distance divided by speed. Based on that math, the system assigns an alarm level. So if the front sensor detects an object closer than 20 centimeters, or if time to collision drops below 1.5 seconds, it triggers a critical alarm. For the blind spots, the sensor looks for the object under 30 centimeters, but I program it so the blind spot warning only turn on when you are driving faster than 20 kilometers per hour, so it does not annoy you while parking. So let's go to the slide 7. To get all this data to the screen, I used a structured UART protocol. Every 10 milliseconds, the microcontroller send two text strings, which are an EV frame with an with the driving data and an ADAS frame with the safety data. A neat trick I used here was splitting the decimal numbers into the separate integer fields. Trying to process the standard floating point numbers takes up too much CPU power on the specific microcontroller. So I split them and keep the system running fast as possible as I can. So in the slide 8, all of the data arrives at the Python dashboard. It gives the driver a live view of everything smooth with a smooth gradient speedometer and a battery capacity tracker, a top-down radar map showing the distance of the objects around the car or the host, and a live readout of motor temperature and torque. Let's go to the slide 9, simulation. You might be wondering why I close to simulate this hardware PICSimLab instead of building it with physical words. Simulating allows me to code and test incredibly fast without worrying about the broken words and the buying new components. More importantly, it is completely safe, so I can test extreme car crashes and battery failures over and over again without breaking any physical hardware. So it is very useful for me and for all of us. I ran into few bugs while I building this. First, my main timer was firing 2000 times too fast, which I fixed by adding a software counter inside my code to slow down the loop to the correct speed. Second, my data stream just randomly stopped working because two parts of my code were fighting over the same timing flag. So I solved this by splitting them into separate flags. Finally, my TTC or time to collision math was throwing an error because variables were not declared in the correct order, and the rewriting the formula top to down fixed it immediately. Let's see the slide 11. Looking back, the coordinating four hardware timers and three sensors purely through C code was a huge learning experience. My biggest takeaways are that you always need to double check your timer math against the actual clock speed of the chip. And I also learned that a clean, predictable text format for your data makes debugging the whole system much easier. This is all about. Now let's see the project demo. This is my Python code. So let's go to the PICSimLab. You can see the PICSimLab simulation. This is the spare parts. This is the output, virtual terminal. These are the readings or data. You can see there are the potentiometers. These are the three sensors, AC sensors. These are the LEDs. This is the accelerator. This is the brake, motor temperature, torque, and this is the buzzer. So let's see the dashboard. So you can see the dashboard here. This is my Python dashboard. So let's take the car for a drive by slowly pressing the accelerator slider. So if I increasing my brake, it will be showing show here, as you can see, 2%, 49%. The speed will decreasing. If I to the 100%, speed will decreasing very slowly. Now check the sensors. You can see collision happening. If the front sensor is too low, then so as you can see on the dashboard, the velocity, torque, and the power matrix respond instantly. The needle movement is perfectly smooth. Motor temperature, as you can see, it, it also working. Now see the left and right sensors. Left and right sensors are also working. Left sensor is also working. Right sensor is also working. When I hit the when I lower the potentiometer, it will show an collision collision happening uh, alert. As you can see, collision warning. LEDs will also respond. ADAS alert. Okay. So look at how the time to collision drops as it crosses the safety threshold. The dashboard triggers a critical alarm. If you look over at the hardware simulation on the left, the red LED lights up perfectly the match. Next, let's check the blind spot. The car is currently moving. Now the car speed is 0 km because the brake is full. The brake potentiometer is fully up. If I down it, then press the accelerator. Then you can see the vehicle metrics here. It is changing and the speed is increasing slowly. You can see the front potentiometer is directly says the collision warning. And if I simulate an overheating motor by dragging the temperature slider, you can see all the way up. The system catches it and logs an over temperature error, enters a safe state. The yellow fault LED turns on. See, the whole demonstration proves that the entire pipeline from the raw hardware sensors and through the C code all the way to the Python does it functioning perfectly in real time. Thank you. And And thank you to the my internship team for their amazing guidance during this internship.